talking about chapter 8 here, which is gases. And we talked obviously about a bunch of different gas laws the previous couple of times. Reminder, we have our Boyle's law. We have our Charles law. Our Guy-Lussac's law. Avogadro. The ideal gas law. Also the combined gas law here. And as we sort of talked about, if you again sort of invest in those two, you pretty much can get all the other gas laws that you need, as we sort of went through using the combined gas law to get pretty much all the rest of these here. We also talked about calculating density of gases and molar mass. And really, there were some dedicated formulas that you could use for that, but really, they really all did sort of boil down to, and they're based off of the ideal gas law. So as we talked about, you could kind of just do a ideal gas law, sort of like a conversion factor problem, and you could get to the density, which is typically grams per liter for density, and obviously grams per mole for our molar mass. Also a reminder, most restrictive in terms of units, so it's got to be atmospheres, got to be liters, has to be moles. R is our gas constant, which you always have. And T would be temperature, which would be in Kelvin. So really, again, these two are really some good ones to know. And again, you can kind of get everybody else from that. Any questions on any of that stuff there? Okay, next thing we're going to talk about is really gas stoichiometry. So the good news about stoichiometry involving gases is it pretty much is the same 4 steps that we used before. You're going to balance the equation. You're going to convert to moles. You're going to do the mole to mole relationship from the equation. And you're going to take those moles and convert it to some other unit. The kind of difference, or how this sort of works with gas stoichiometry, is somewhere along the way you will use PV equals nRT. So somewhere along the way, usually you'll use the ideal gas law in your stoichiometry problem. If you use it up front, sort of the second step, you typically would be solving for moles. So N would equal PV over RT. Most commonly, though, it is used sort of on that last step there. And on the last step, typically you'd be solving for volume. Oftentimes you are interested in sort of the volume of a gas that you collected. So really all the intermediate steps are going to be the same. In addition, you could have a limiting reagent type problem as well. Very rare, but you could potentially have a limiting reagent sort of situation that could have dealt with a gas problem. But I would say probably 9 times out of 10, it's just going to be really a basic stoichiometry problem where you will really interject either the gas law at the end, which is very common, or the gas law at the beginning. Occasionally, you might even use them both at the same time in a problem, but that's sort of rare and that type of thing. So let's take a look at one here and see. So we want to know what volume of CO2 produced at 37 degrees Celsius and 1 atmosphere when we react 5 grams of glucose in this reaction. So why don't you take a couple of minutes and work it out? Let me give you some numbers. Carbon 12.01, hydrogen. Okay, let's take a look. So again, this is a stoichiometry problem. It's involving gases. We are looking for a volume of a gas. I'll sort of see. We have the ideal gas law, PV equals nRT. We always have R. We do have the temperature given to us. We also do have the pressure. We are looking for volume at the end, which means for CO2, really the only thing we're sort of missing is the moles of CO2. So where the moles of CO2 is going to come from is really the stoichiometry part of the calculation. And really the only other piece of information that's given to us is we're going to start with 5.6 grams of glucose. So we'll start our stoichiometry problem like normal. We obviously have an equation, it's balanced. We're going to take what they gave us, which is 5.60 grams of glucose. We'll need to convert this into moles. So going to the periodic table and adding up all the parts there, looks like a $180.2 grams per mole here of C6H12O6. And if you got a number at this point, 180.2 gets us something like 0.0310766 moles here of C6H12O6. Now we do want to again get to moles of the CO2, so we can use the ideal gas law. So we'll do really step number 3 here, which is the mole to mole relationship. So from the equation, we have 1 mole of glucose and 6 moles of CO2. So putting the CO2 up on top gives us 6 moles of CO2 to our 1 mole of glucose here. Moles of glucose will cancel. We're going to times this by 6 basically, and we will end up here with 0.1865 moles of CO2. So really here, the kind of middle part of this problem is really just a basic stoichiometry problem. The difference here is going to come at the end. So instead of at this point where we a lot of times would use the molar math to get how many grams that would be, we're going to actually use our ideal gas law here to figure out the volume. So once again here, PV equals nRT, solving for V, nRT over P. We do have to do a little bit of work here. We got to convert our temperature into Kelvin. So that's a 37 and a 273. That's a 310 move there. I think we're good on everybody else. We have atmospheres. So our moles we just calculated 0.1865. Our gas constant, which we always have. And our temperature there in Kelvin, squeeze it in, and divide it by our pressure, which in this case is 1. That's not too bad. So moles will cancel, Kelvin will cancel, atmospheres will cancel, leaves us liters, and we will end up with looks like 4.74 liters in this case of CO2 would be produced. That would technically be the theoretical yield of CO2 in liters in this example here. So it really is the same sort of 4 steps. The difference here is actually step number 4. Instead of using the molar mass, we are going to use ideal gas law. And I would say probably 9 times out of 10, that's probably where you would use it. Again, if you use it earlier on, it would be solving for moles and then maybe a regular stoichiometry problem at the end of it. Any questions on any part of that there? Yeah. Would I like, I'm sorry? You should include units throughout the whole bar, not just numbers and stuff. Yeah. Other questions? All right, let's try maybe another one here. This one we're going to do one of these days, I think. Next week, I think. We take some magnesium, we react it with some hydrochloric acid. We want to know how much hydrogen gas will we collect at STP. If we started with 5 grams of magnesium, magnesium should be 2431, I think. Hydrogen is 1.008, in case you need. Okay, let's take a look. So once again, we are looking for the volume of hydrogen gas at STP. Remember, STP does stand for really 2 values. The temperature is 273 Kelvin, and the pressure is 1 atmosphere. So we can think about, again, the ideal gas law here for H2. And once again, we do have temperature, we do have pressure, we always have R. Once again, we are looking for volume. So we are going to use stoichiometry here to get to the moles. And we would do that using the magnesium. So we'll start with converting the magnesium here into moles using the molar mass from the periodic table, 24.31 grams per mole. We really don't want magnesium. We do want to get to hydrogen, so we can do the mole-to-mole relationship next. And in this case, it's a pretty simple one. It is a 1-to-1 relationship, which means we take 1 mole of magnesium on the bottom and 1 mole of hydrogen up on top. And that will get us something. 5 divided by 24, 31. Gets us, we'll call it 0.206 moles of hydrogen. We now have solved for really hydrogen. So if we wanted to use the ideal gas law, we could. Once again, here we would be solving for volume, which would be nRT over P, bringing P to the other side, dividing. Putting in our numbers here, we would get 0.206 moles, our R 0.08206 liters atmosphere, Kelvin a mole. Our temperature, which is 273 Kelvin, all divided by our pressure of 1 atmosphere. Atmospheres cancel, moles cancel, Kelvin cancel, leaves us with liters. And we would get 0.206 times 0.08206 times the 273, about 4.61 liters of H2 would be collected here. First off, any question on that calculation? Could I have solved it a different way? I could have probably, otherwise I probably wouldn't have asked, but we are at STP conditions. So remember that when you are at STP conditions, there's that conversion we talked about, that 1 mole of any gas will equal 22.414 liters, which means really you could have just picked up at this point and used that conversion. That 1 mole of hydrogen would equal 22.414 liters there at STP. And pretty much will give you the same answer, maybe slightly different, a little bit of rounding, but pretty much the same guy there, 22.414, about 4.62 maybe with some rounding. So pretty much the same guy as you went there. So that's a case where you could use that conversion that we talked about. Remember that you could only use that conversion if it is at STP conditions. You cannot use it if it's not at STP conditions. The ideal gas law you could use under any conditions, STP, non-STP conditions. So if you don't want to worry about it, like we talked about earlier, you can just always go into the ideal gas law and you'll get the same answer. Any questions on that? Any questions on gas stoichiometry here? One last thing about gas stoichiometry before we move on, that we talked about earlier, just to revisit here, which was sort of the relationship that we see with Avogadro's law. So if we had a reaction such as this one here, we'll do a 2 there and a 3 there. And let's say that we started with 5 liters of H2 and we wanted to know how many liters of NH3 would we produce at, we'll just make up some temperatures here. We'll go 295 Kelvin and 1.35 atmospheres. So this again is a really gas stoichiometry problem. And you could approach it exactly the way we basically just did these last ones. In this particular case, though, we're actually starting with a volume of a gas, and we're looking for obviously the volume of another gas. So we really don't have any grams or anything like that. So this would be a case where you would actually use or could use the ideal gas law up front in the calculation. So we have our balance equation, And the second step is for hydrogen, PV equals nRT. We have pretty much all of that information. We have the temperature, we have R, we have the pressure and the volume. So that will allow us to get some moles for the nitrogen. And if we did that, the moles for hydrogen, the moles for hydrogen would be PV over RT, dividing these guys to the other side. Putting in our values for hydrogen, we have a pressure that is 1.35 atmospheres. We have a volume that is 5 liters. We have our R. And we have our temperature, which was 295 Kelvin in this case. And if we do all that there, 1.35 times 5 divided by 0.08206 divided by 295 gets us 0.2788 moles of H2. Now, again, we're interested in NH3, so we can continue on at this point. So a little bit different than going grams to moles, using the ideal gas law to get the moles at this point. We then can do our mole to mole relationship to get to NH3. So taking our 0.2788 moles of H2, looking at the equation, it is a 3-to-2 relationship between those two. So 3 moles of H2 to 2 moles of NH3. And if we do that, we'll take our number, times it by 2 and divide it by 3. Basically gives us 0.186 moles of NH3. Now we're really at step number 4. And for step number 4, we now can once again use PV equals nRT and solve for V for NH3, which would be nRT over P. We could use our moles that we just calculated. We could use the ideal gas, not the ideal gas, we could use the gas constant there. The pressure and temperature is basically the same as what we had earlier. So we'll use the same values here. So our temperature would be 295 and our pressure there would be 1.35 atmospheres. So taking our value, 0.08206 times the 295 divided by 1.35, going to get us about 3.33 liters of NH3. So this is an example where we would use we could use, I'll put it that way, the ideal gas law up front to figure out moles. And then we could also use on the back end of the calculation to figure out volume. First off, any question on doing it that way there? Now, where this can be very much shortcutted in terms of the calculation is applying what we talked about with Avogadro's law, which is as the volume increases, basically the moles do. So you got 1 vol, you got 1 mole, you got 2 volumes, you got 2 moles. And basically this was at constant pressure and temperature, which is basically the situation that you need for Avogadro's law. So because of that, what we could do, if you remember, is we could go to sort of the equation, and instead of doing a mole to mole relationship, we could do a like volume to volume relationship, the exact same way that we do the mole to mole relationship. So just like we did that there are 3 moles of H2 gives us 2 moles of NH3, we can, because of the constant pressure and temperature here, just strictly go right into 3 liters of H2 would give us 2 liters of NH3. The 3 and the 2 are still just the coefficients here. So that's basically where they come from, which means pretty much once we got to this point, actually, we don't even need to get to that point. We could actually start with our volume at the very beginning, which would be 5 liters of H2. And using our volume to volume relationship here, 3 liters of H2 gives us 2 liters of NH3. And with one step here, we could basically get the correct answer of 3.33 33 liters. So you can see it's a much shorter approach this way. And you can only, again, do it if it is obviously gases and you are at constant temperature and pressure. Otherwise, you really can't do this. So the top part is really the long version of that calculation. That's basically the short version of that calculation, and they both get you there. Any questions on either part of that there? Yeah. You can, yeah. So if it is under constant pressure and temperature, basically, and then the gases, basically Avogadro's sort of law kicks into place. And basically, they're sort of equivalent in that situation. The number of moles you have would be the same number of volumes that you had. In this case, we did liters to liters in terms of the volumes. Yeah. Other questions? Okay. So that obviously is stoichiometry. The next thing we're going to talk about then is partial pressures, or Dalton's law, partial pressures. And it does sound quite difficult, but it's sort of a straightforward sort of concept. If we have a container that has, say, just one gas molecule in there, one type of gas molecule, then the total pressure is basically all from that one type of gas molecule that's flying around. So the pressure of A there would be basically the contributor to the total pressure of that mixture, or not really, of that container. If we have a container where there are multiple gas molecules in there flying around, they each are going to basically contribute to the overall pressure of that mixture. And that means that the total pressure here would be the pressure of A plus the pressure of B plus the pressure of C in this case. And these are what are known as partial pressures because they partially contribute to the overall pressure. By the way, the total pressure is the atmospheric pressure, and it's like the barometer reading. If you were doing an experiment, it would be the barometer reading that you would take. Now, how do we get to the pressure for each of these things? A couple of things that we take into account here. One thing is the idea that these gases behave ideally. And what that essentially means is there's really no interaction between different gas molecules in an ideal situation. So even though there's multiple different gas molecules flying around in the container, we could basically assume that they're kind of in there by themselves, basically. So we basically could do 3 separate problems to figure out the pressure of each of these gases. And we basically would use the ideal gas law in each case is the most common way, where you would solve for P for each of the gases that would be there. So you basically would just do 3 separate ideal gas law calculations, and that would give you the partial pressures of each of those gases. And then you simply would add them all together to get the total pressure. Another nice aspect of sort of the mixture of gases is they're pretty much all in the same container, which means they all have the same volume and they all have the same temperature. So the volume and the temperature is pretty much the same for all gases that are there. And that means if you look at the ideal gas law, you pretty much have temperature and volume and R. So really the only thing that's going to be different in each of the individual partial pressure calculations is basically the moles of the gas. So everybody else will pretty much be the same. You obviously, again, need to make sure you get everybody into the right units when you do that. Any questions on that there? All right, so that's basically what we just talked about. Now, there is another situation that could occur, and that's a situation where maybe you are not given enough information to kind of go into the ideal gas law. So maybe you're not giving temperatures, you're not given volumes or things like that, but you are given the moles of all the gases that are there or the grams of all the gases that are there. So if you are given the moles of all the gases or a total pressure or a partial pressure, you can still calculate the total pressure or partial pressure by using this equation here. This is the partial pressure of a gas equals the mole fraction of that gas, which we talked about, I think, in the previous chapter. Reminder, this is a mole fraction calculation. You take the moles of the gas you're interested in and you divide it by the total moles. You just don't multiply it by 100. So it's kind of like a percentage without the percentage part of it. And this is the total pressure. So basically, if you are able to get to the moles of all the gases that are there, and you basically just need one pressure value, either the total pressure or somebody's partial pressure, you'll be able to figure out the partial pressure of all the other gases. You could also figure out the total pressure in that particular case. So those are two ways that you can sort of calculate the partial pressure here. Any questions on that there? This is a mole fraction. Yeah. So we talked about, I think, in the last chapter, but again, you just basically take the moles of the gas you're interested in and you divide it by the total number of moles that are in the mixture. You just don't times it by 100, though. There are questions? All right, so let's take a look at maybe one here. All right, we have 5 grams of helium, 5 grams of neon in a 2.5 liter container at 27 degrees Celsius. What are the partial pressures of each gas and the total pressure of that mixture? So helium, I think, still 4.003. And neon, I think, is like a 2018 we'll go with. So we're looking for 3 things: the partial pressure of helium, the partial pressure of neon, and our total pressure, basically. All right, so it'll take a few minutes to see what you come up with here. Okay, let's take a look. So we basically got both of these guys flying around in the same container. Again, we could assume under ideal conditions that, they're kind of like in there by themselves. So we're basically just going to do the ideal gas law really for each of them. We're going to solve for P for each of them, which will give us nRT over V. We do have our volume right there. We do have our temperature, which we already know we do need to convert to Kelvin. So might as well just do that right now. Gives us 300 Kelvin. And again, really, as we talked about, really the only difference in each of these calculations is going to be the moles. So we might as well start there. So for helium, we'll take our 5 grams. We'll divide it by the molar mass from the periodic table, 4.003 grams per mole. We'll do the same thing here for neon, which also is 5 grams. And using the molar mass there for neon, which is 2018 grams per mole. Going to give us 5 divided by 4.003, 1.249, we'll call it. We'll call it 1.25. And 5 divided by 2018.248 moles of neon. So really at this point, we do have everything that we need to calculate it. So just kind of 2 individual calculations here, starting with, we'll do helium, which would again give us nRT divided by V. So using the moles of helium, 1.25, our gas constant, 0.08206, our temperature, which was 300 Kelvin, all divided by our volume, which was 2.5 liters. All the units cancel except for atmospheres, which is good because we're looking for a pressure. And we end up with 1.25 times 0.08, 1.25 times 0.08206 times the 300 divided by 2.5. We get 12.3 atmospheres. This would be considered the partial pressure of helium, would be that number. We're going to do pretty much the identical calculation here for neon. Putting in the values for neon, our moles 0.248 R. Again, it's going to be the same temperature as they're in the same container, and it will be the same volume as they are in the same container. That is going to get us here looks like 2.44 atmospheres. That would be considered the partial pressure of neon in this case. First off, any question on either of those calculations? To find our total pressure, then we will basically just add those together. So the partial pressure of helium plus the partial pressure of neon, that's going to give us a 12.3 atmospheres plus a 2.44 atmospheres. And that gives us 14.7 atmospheres. Any questions on that there? The major contributor to the pressure in this case is which one? Is helium by a long shot. And that is because, as we will talk about shortly, helium is lighter, which means it will be moving a lot faster. So because it's moving a lot faster, it'll be causing a lot more collisions. And that's why it accounts for more pressure in this particular mixture. Any questions on partial pressure? So really just sort of an ideal gas law added together. Take a look at another one here if everybody's good. So in this case, we have a sample natural gas. It contains 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of propane. The total pressure is one given, temperatures or volumes, but we do have the moles of all the gases that are in this mixture. So we could use that other equation or formula that we saw, which is the partial pressure of a gas is equal to the mole fraction of that guy times the total pressure. And we do have all that information basically given to us, or we could calculate it. So in this case, we're interested in propane. So we basically do the mole fraction of propane, C3H8. So that would be the moles of propane up on top, divided by our total moles, which basically is just everybody added together, plus 0.116. And if we do all that, I think you get 8.77, something like that, 0.116 divided by 8.24 plus 0.421 and plus 0.116. Going to give us basically a mole fraction of 0.0132. Remember, we don't multiply by 100, but basically it's like 1.3% of the mixture is this propane. We're then going to take the total pressure, which was given to us. And now we can get the partial pressure here of propane would be our mole fraction times our total pressure. And that would get us 1.37. Basically, we'll call it 0.0181 atmospheres. We then could, if we wanted to, do the exact same calculation for methane, get the mole fraction times by the total pressure, and also ethane as well. Basically the same sort of steps there. Any questions on that one? So that's a nice convenient one. Again, in case you're maybe not given enough information to use the ideal gas law. Again, you could use this equation as long as you have the ability to get the moles of all the guys that are in the mixture, and you got one pressure information given to you, either the total pressure or even one person's partial pressure would be all you would need in this particular case. Any questions on that one there? Another really important sort of partial pressure situation that occurs a lot of time in the laboratory is when we do collect gases, oftentimes we displace water in the process of doing so. So in this case, when you heat up the potassium chlorate, the oxygen gas is generated, follows through the tube, comes into your big jar there, though it's full of water to begin with. So as the gas comes into the jar, the water comes out of the jar, and you end up with this empty space here. It's really not empty. It actually, in this particular example, has the oxygen gas is basically filled in that empty spot. But as a consequence of doing this reaction in water, when we kind of do a reaction, it probably generates a little bit of heat. Heat and water will also produce some water vapor. So we'll also get some water vapor that will actually come along for the ride. It's not really any part of the actual reaction that's taking place. It's just, again, a consequence of how you collected the actual gas. So in a lot of cases, we are not really interested in the pressure that's being contributed by the water vapor that we're collecting. So what we have here is sort of a partial pressure situation where the total pressure is equal to the pressure of the gas you're interested in, plus the vapor pressure of water. The vapor pressure of water is usually a value that you can look up on a table, one of those things, a table that's on paper, one of those things there. So the vapor pressure of water, usually you can look it up in a table based on temperature. So a lot of times what we end up doing with this is it becomes a very simple subtraction sort of thing. We really want the pressure of the gas by itself. So we take the total pressure, which is the atmospheric pressure or the barometer reading, and we subtract off the vapor pressure that we looked up in the table. This will give us just the pressure of the gas that we're actually collecting as a result of the experiment, sometimes referred to as the pressure of the dry gas because you subtracted off like water's sort of contribution to it. Any questions on that? Yeah. It is dependent on the temperature. So it does, if your question, it does change depending on the temperature. So typically you would go to a table and a lot of times just look it up based on the temperature and it will give you basically the vapor pressure of water. And you basically, it's sort of like a correction value, again, just to get to the pressure of just the gas you're interested in, because usually you will continue on with calculations and you want to use really just the pressure associated with the gas you were doing in the experiment when you maybe put it into a gas law or something like that. All right, so here's an example of a table of water vapor pressure. And as your question was there, you can see as the temperature changes, so there's the value that you can look up and find. So if we look at one here, we have a sample of oxygen gas that's saturated with water vapor at 30 degrees Celsius. The total pressure is 750 torr. The vapor pressure of water at 30 degrees Celsius is 31.824 torr. What is the partial pressure of oxygen? So this is definitely what we were just talking about. We basically collected the gas over water. These are the key words that you typically see in a textbook problem. It mentions something like it was saturated with water vapor. It mentions something like you collected it over water or something to do with water in the collection of your gas. And that should tell you that you got basically this situation happening here, that the pressure of the gas plus the vapor pressure of water. In this particular case, they gave us the total pressure, which is 753 torr. We're looking for the pressure of the oxygen gas, and they were nice enough to give us the value from the table there by looking it up, and that was 31.824 torr. So the pressure of oxygen here would basically be 753 minus 31.824 torr, and that would get us about 721 torr. In this particular case, they did want the final answer in atmospheres. So a reminder, as we go from torr to atmospheres, we will divide by 760 to do so. And if we do that, we end up with 0.949 atmospheres. So this would represent basically the partial or the pressure of the oxygen gas, the dry oxygen gas that we basically kind of subtracted off the water vapor pressure. So that's a fairly simple one. It's sort of a subtraction one, but it's very necessary as we go into our gas experiments. You'll have to do that as well for a couple of them. Maybe I think one of them at least, that you also subtract off sort of the water vapor pressure. Any questions on that there? Yeah. The 760. It probably will be given to you, but it's really a number you should kind of know, use it a lot, but it probably will be there somewhere. Yeah. Other questions? Yeah. All right. So let's talk a little bit about the kinetic molecular theory of gases. A gas is composed of molecules that are separated by distance. The molecules are considered to be points. And one of the things that makes, again, something an ideal gas is really this first one. They possess mass, but they have a negligible volume. So if you think about a lot of gas law sort of problems that we come across, they oftentimes will talk about the volume of the container that the gas is in rather than the volume of the gas molecules itself. So the gas molecules volume is very small compared to the container they're flying around in. So because we assume that they are flying around and sort of filling that container uniformly, we do look towards the volume of the container rather than the gas itself in an ideal situation. Gas molecules are in constant motion. As they collide, they're perfectly elastic, which means, they're not really being stuck to each other or anything like that. They'll pop off of each other. Number 3 here is the second thing that makes something an ideal gas is under normal ideal conditions, there's no attractive forces or repulsive forces between gas molecules. That's essentially why in the problems we just did, even though they have different gas molecules in the same container, we can kind of look at them as being in there by themselves because there's really no interaction between them. Why would that make a difference? If there was interaction, well, clearly a gas molecule would be free to bounce around and hit the container very much. And if there was some attractive force, for example, between this gas molecule and the one going towards the wall, it may slow it down, which would impact obviously the number of collisions and also impact the pressure, or it may repel it and actually send it the opposite way and also affects the pressure. So under ideal gases, there's really no interaction between these gas molecules, as we'll talk about later on here. Really does only occur when you get really large pressures and very small temperatures. Then you do have to kind of take those things into account. But under normal sort of conditions that we deal with in sort of normal room temperature type conditions and pressures, there's really an ideal situation where gases basically behave that way. The average kinetic energy increases. So as we talked about, if you increase the temperature, you will see a gas molecule start to move faster. And obviously, if you lower the temperature, we will see it sort of move a little bit slower. So these are, again, some of the relationships that we talked about through the different gas laws. We saw with Boyle's law, again, that sort of inverse relationship. As the pressure goes up, the volume goes down and vice versa. Charles' law and Guy-Lussac's law, we saw again in a fixed volume. If you increase the temperature, you will see the pressure start to increase because the volume's not moving. And if you lower the temperature, you'll see the pressure start to come down, again, because the volume doesn't move. In sort of Charles' law situation, we do see the adjustment of the volume. And again, that is how it's able to keep constant pressure. So as the temperature goes up, so does the volume, which allows the number of collisions to remain relatively constant and also keeps the pressure relatively constant. And obviously the opposite there if you went the other way. As we talked about, basically the pressure is proportional to the number of moles of gases in Avogadro's law. And as we saw with Dalton's law of partial pressure, under these sort of ideal conditions with no attractive or repulsion forces, the pressure of one gas is not dependent at all by the other gases that are in there with it. We again is basically can just think of them as being in there by themselves. So let's talk a little bit about the speed of a gas. So this is nitrogen gas at 3 different temperatures. And what we see is at the lower temperature, the average speed is somewhere around here. When we increase the temperature to about 300, the speed starts to get a little higher. And when we increase it to 700, we see a much higher sort of velocity. So that correlates to what we talked about, that as you increase the temperature, we do see the gas molecules move faster. And obviously, if you lower it, the opposite trend would happen as you go that way. Now, when we look at actually different gases at the same temperature, what we do see is chlorine is moving about this fast. Nitrogen is moving about that fast. And helium is moving about that fast. And what we see here is as the molar mass starts to decrease, we do see that the gas molecules are moving faster. And that's again what we kind of saw there with that partial pressure problem between the helium and the neon, with the helium being lighter, moving faster, causing more collisions, and thus causing more pressures. You can actually calculate the root mean square velocity of a gas, and that's what that is on the bottom. That is RMS, which stands for the root mean square velocity. And it equals the square root of 3 times RT times the molar mass. So these are a couple of different things. T is our temperature in Kelvin. The molar mass here is actually needs to be in units of kilograms per mole rather than grams per mole. And the reason for that is the R that we use here is actually the energy R, which is 8.314 joules per Kelvin per mole. And a relationship is a joule is equal to a kilogram meter squared second squared. So that is what a joule equals. And that is really why the molar mass here actually needs to be in kilograms, so all the units cancel out correctly. If we just look at the units here, we would have kilograms, meters squared, second squared, Kelvin and mole. That would be our R. We would have our temperature, which is Kelvin, and we would divide it by kilograms per mole. That's all square rooted. So the Kelvin would cancel, the moles would cancel, the kilograms would cancel. That would leave you meters squared over second squared, which if you take the square root of that, will leave you in a velocity of meters per second. The good news is the R value number doesn't change, just, the joule represents a kilogram, meter squared, second squared, which means, again, you do need to get those guys into the proper units. So why don't we try to calculate the what we saw there? Let's do it on here. So let's calculate the RMS for our two gases we did earlier, neon and helium, at 300 Kelvin, which is what the conditions were there, and see what you come up with. So calculate the root mean squared velocity here in meters per second. Again, it is the square root of 3 RT over the molar mass. All right, take a moment or two to see what you come up with here. Once again, neon is 4.003, and okay, let's take a look. So for helium here, our root mean squared velocity will equal square root of 3 times 8.314. Again, it really is joules per Kelvin per mole, but that joules is a kilogram meter squared second squared, which is where those guys come from, times our temperature, which is already in Kelvin. And by the way, it does need to be in Kelvin for it to cancel out correctly with the Kelvin that is here. So that definitely does need to be there. Once again, because really that joule is a kilogram meter squared second squared, we do need to convert our grams per mole into kilograms per mole, which means we're going to move the decimal place 3 places to the left or divide by 1,000. Here, the moles will cancel, the Kelvin will cancel, the kilograms will cancel. That really does leave us meters squared over second squared, which becomes meters per second when we take the square root. And we will end up with here looks like we'll call it 1,367 meters per second would be the root mean square velocity of helium. We do our same calculation here for neon. It's almost identical, except for obviously the molar mass here. So we'll do our 3 times our 8.314 joules per Kelvin per mole, our 300 Kelvin, and once again, kilograms, meters squared, second squared on that guy. that is going to be also divided by 1,000, which gets us 0.02018 kilograms per mole. And that would get us 3 times 8.314 times 300 divided by 0.02018. Probably should take the square root of it, would be good as well. Let me try that again. Like that number seems a little too big. Let's try it here. Now I'll take a little square root. There we go. About 609 meters per second. So we see here that helium in that example where we did the partial pressure problem is moving approximately twice or so as fast as our neon. And again, that would be light. It accounted for a big majority of the pressure that we saw in that particular problem. Any questions on that? Yeah. It's a gas constant. So the gas constant that we use for most of the gas laws is this one. But there is a gas constant that is used more for like energy, and it is this version. And again, it is also a value that you just have available to you as well. You do not want to use this one in the other gas laws. Otherwise, you have a lot more conversions to do that you don't want to do. So this one strictly so far for us here would be for this particular one. And really it's because of the joules part that it is kilograms, meters squared, seconds squared. And that's how we kind of get to the proper units for the velocity. It comes from there. So you want to use, obviously, the proper R value, but they're both constants and they both the same number. Other questions? Okay. Now, next thing we're going to talk about a little bit here is gas diffusion. So gas diffusion is the gradual mixing of molecules of one gas with molecules of another based on their properties. So here we have a bottle of ammonia and we have a bottle of hydrogen chloride gas or hydrochloric acid, really. And when they come together, they make ammonium chloride, which is this white sort of powder that you can kind of see there, I think. So the question is, why is the mixing happening right about here? Why is the mixing not like in the center or towards the ammonia? Why? It actually has to do with what we were just sort of talking about a second ago. When we look at ammonia, it's 17 grams per mole, which means if you did its velocity, it actually would be a much faster velocity, right, than the heavier HCl. So that means the HCl is coming out of the bottle, but the NH3 is already moving a lot faster. So the NH3, because it's lighter, will have a higher velocity, and it's able to actually move itself over to the other side. And that's why the mixing occurs there on the right-hand side, closer to the slower moving hydrogen chloride gas. You can actually calculate those things. This is R1 over R2. So that's the rate of one gas versus the rate of another equals the molar mass of one gas versus the other, basically. And you take the square root of it. So gas diffusion is that gradual mixing of two different gas molecules based on their properties. Gas effusion is the process where one gas that's under pressure in one compartment basically will come out into another compartment, passing through a small opening. So these guys will pop out through that hole to the other side. We basically have our same sort of formula as we saw over there, which is rate 1 over rate 2 is equal to T2 over T1. Those would be times, and the other ones would be rates. Our molar mass 2 and our molar mass 1. So we can use these to calculate things like the molar mass of an unknown based on how fast it is moving compared to maybe a known gas. And that's sort of what the problem down here is. Nickel forms a gaseous compound that is NiCOX. What is the value of X if under the same conditions CH4 effuses 3.3 times faster than the compound, the nickel compound? So we could do a couple of things here. We could call M1 the molar mass of the nickel compound. You could call M2 the molar mass of CH4, which we can calculate. So let's just calculate that real quick. 12.01 plus 4 times 1.008. So that is the molar mass of 16.04 grams per mole. And that obviously is our CH4's molar mass. We know that R1 is the rate of our nickel compound, and we know that R2 is the rate of our methane, which actually effuses 3.3 times faster than the nickel compound, which means this one is 3.3 times R1 in this particular case. So we do have everything that we kind of need here. We could do our R1 over our 3.3 of R1. So that's basically our rate 1, and the rate 2 is 3.3 times faster than rate 1, equals the square root of molar mass 2, which was 1604. That's our methane. And really our unknown molar mass here, which is our M1. So when we do this and this cancels, gives us 1 over 3.3 is equal to the square root of 16.04 grams per mole over M1. To get rid of the square root on the right, we are going to square both sides. So we take 1 divided by 3.3, and then we're going to square it. Gives us 0.09182 equals 16.04 over M1. Multiplying the M1 to the other side and dividing the other guy over gives us M1 would equal 16.04 grams per mole divided by 0.09182. So that gives us a molar mass for our unknown compound of 174 we'll call it 7 grams per mole. Any questions on how we got there? So how this is going to help us sort of figure out what the formula is if we look at the formula, which is Ni, CO, and X. The one thing we know for sure is when we take this all together, it should equal 174.7 grams per mole. We know for sure we have 1 nickel, so we could go to the periodic table and get the molar mass of nickel, which I can't see from here. Is anybody can see that? That's at 50 something, 54 maybe. And anyway, with the periodic table, nickel. 58.69, 68.59. Try it one more time. Okay, so it was 58.69. Okay, sounds good. 58.69. We'll do that. All right, give or take whatever. There minus 58.69 tells us that we have about 115.98 grams is made up of these carbon oxygen units. So we know each carbon oxygen unit is 12.01 plus 16, that's 2801. So 2801 is the molar mass of carbon and oxygen together, which means if we take about 116 and divide it by 2801, it gives us about 4.1, which is close enough to round to 4. So our missing guy here would actually be 4 in this case, and it would be NiCO4 would be our missing compound here. So in this case, we could use the different rates and how they're diffusing or effusing to figure out the molar mass of an unknown compound, and also figure out obviously the molecular formula of it. Any questions on it there?